to draw the graphs for AC and DC. So we know AC alternates, as the name suggests, a AC alternating current. So it alternates like that. So what we see now is that it is actually changing direction over time. So this is what we would see for the graph of AC. Right? Once it crosses this zero line, we're talking about AC. While for DC now, right, we might have something like this. Something like this. Right? So this is DC. So once it doesn't cross the zero line, that's DC. You can also see DC in terms of a straight line across. This is typically what you will see from a brand new battery. Right? So these are the graphs of AC and DC. So we need to know these things. We need to know also the different parameters. Because for the AC, we can talk about a peak current, which will be at the top right here. So the peak current. Right? So once you want to know the peak current, I mean, you just read off. So let us say this was probably 5, and this is current in amperes. So your peak current would be 5 amperes. You also want to know the period, which is the time to make this figure right here, this S-looking figure. So that would be your period, and whatever this is, let us say this is maybe 0.25, and this is time in milliseconds. So your period will be 0.25 milliseconds, and then from that now, you might be asked to find, okay, what is the frequency, and so on. So I'm kind of going through these things. Again, as I said, we're going to be looking at some questions to see if we can apply some of these concepts. So I'm just kind of quickly giving us an overview, and then we're going to then see how we can apply what we would have been talking about. So just as we talk about a peak current right here, this right here will also be a peak current, but it's going to be a negative peak. So it's going to be -5. Sometimes they might ask you, okay, what is the peak to peak current? Now the peak to peak is always 2 times the peak current. So we're going to see if we can come across questions like that, and we're going to see how we would apply ourselves with those questions. All right, so we need to know the types of current, right? We need to know what's that thing called again? We need to know electrical quantities. Electrical quantity. Just give me a second. Yeah, so we need to know our electrical quantities. So these things include resistance, right? Resistance, which is measured in ohms. So I'm just going to talk about the quantity as well as the unit real quick. So we need to know resistance. We need to know electric current. Which is measured in amperes. We need to know potential difference. And we need to be able to define these terms. So potential difference. Potential difference, right? PD, right? We need to know potential difference. We need to know things like EMF, right? Electromotive force, which is, oh, well, I should give it a unit. So potential difference is measured in volts. EMF is also measured in volts right here. We need to know things like electric power, right? So we need to know power and the different formulas. So power is measured in watts, and the different formulas for power include P equal IV, P is equal to I squared R, and P is equal to V squared over R. So we need to know those things. What else? So resistance, current, potential difference, power. Yes, we need to know energy as well. Electrical energy, which is measured in joules, right? And we need to be able to write expressions for energy that relates energy and potential difference, which is this expression right here. We'll say that E is equal to QV. And also, as I mentioned, Q right here. Let me just put it right here. We talked about it earlier. So Q, sorry, not Q. electric charge, which is measured in coulombs, and the symbol is Q. So this expression right here relates the electric charge to the potential difference. So it says that the energy is equal to the electric charge multiplied by the potential difference. So these are some things that we also need to be aware of as we are, reviewing the topic of electricity and magnetism. Again, as I said, I'm going through these things, and then I'm going to see if I can actually pull on a question for us to go through to see how much of these concepts, we can actually apply to that question. So that's that. Anything else I'm left leaving out? All right, so that's pretty much that. By the way, how we feel so far? What are you feeling so far? Because I know I'm kind of going fast with this, so let me know how we're feeling so far. Are you okay?
Yes, sir.
Okay.
Yes, sir.
All right, cool. So also now we need to be aware of circuit symbols. So we need to know about our different circuit symbols. So from the very basic, a simple cell like that to a battery, right? Need to know these measuring instruments, your ammeter, your voltmeter, oftentimes they bring this one, the galvanometer, right? Or sometimes they represent it as this with a little arrow. So you need to know those symbols. What else? You need to know your resistor symbol, right? If you're doing electricity, you must know the resistor or this variation. You need to know these. Again, bear with me as I go through quickly. This is basically sort of a recap, so to speak. Just quickly, and then we're going to apply some questions.
Sir.
Yes, Samuels.
Wait up, be confused. What me lost? Me know where to talk about. I swear to you.
As I said, what we're looking at the overview of electricity. Just touching on some of the key things that we need to be aware of. So I'm going through quickly, just recapping or sort of setting the stage, and then we're going to see how many of these concepts we can actually apply to a question. All right? Cool?
Yes, sir.
So let me just, to be fair, let me just give the names of these symbols as I'm going through. So this is the cell, battery, this is the ammeter, this is the volt, V-O-L-T, meter. This we say now is the galvanometer. Sorry, my pen kind of lagging up. Galvanometer. These are resistors. So that's the resistor. We also need to know of this symbol right here. Especially, when we talk about rectification, we need to know this thing, which is a diode. Also, we need to know a simple switch, like that. Need to know this one right here, variable resistor. So we need to know that, variable resistor. We need to know the fuse, right? You have two different representation. This one, or this one. Need to know the fuse, need to know a lamp, which is like that. Need to know this representation as well, so something like that. So we need to know these. And these are the more fundamental ones. So again, this is a diode, a switch, a rheostat, which is a variable resistor. So if you simply say rheostat or variable resistor, they'll give you the mark for that. Need to know the fuse as well. Filament lamp, or the bulb. So for those persons just joining on, we're kind of going through a quick overview of one second. Check description. Alright, so we're just kind of doing a quick overview, and then we're going to see if we can run one or two questions related to this, to see if we can get some context of what these are all about. So it might seem as if I'm going through quickly, which in fact I am, and it's just to kind of set the foundation as to what we should be aware of. Alright, circuit symbols. Next thing we need to know now, next major thing that we need to be aware of is Ohm's law. So Ohm's law, should be able to define it, right? Should be able to define it, and I'm going to just quickly define it here. So Ohm's law says that the current through a conductor is directly proportional to the PD, which we know is potential difference across its ends, provided temperature is kept constant. So that's Ohm's law. So should be comfortable with that. So again, we're just kind of quickly going through, touching the surface of what we should know, and then we're going to look at some questions later on. So need to know Ohm's law, and we also need to be able to, from the definition of Ohm's law, we need to now be able to write the mathematical expression for Ohm's law. So since we say that the current through a conductor is directly proportional to the potential difference across its ends, we can write an equation where we say that the current I is directly proportional to the potential difference. So we can say that I, let me put it in the middle right here. For this part, don't need to show this, but just for relatability with the definition and the formula, just to see that, okay, from the definition, we can derive the formula. So the formula says that the current is directly proportional to the potential difference. So if current is directly proportional to potential difference, we can say that I is directly proportional to the potential difference, which is, the symbol is V. So I is directly proportional to the potential difference. Now what we see now is that we can replace this directly proportional symbol with equal sign and introduce a constant. So the constant we introduce is the resistance. So we get I is equal to V, but V now, and we're going to introduce a constant R, which is the resistance. Now what we see now is that the resistance is inversely proportional to the current. So we get I is equal to V over R. So this is what we need to be most concerned with when it comes down to Ohm's law. I is equal to V over R, or I prefer to write it this way because I tend to be able to remember it better this way. V is equal to IR, because I just remember Vir. So we need to know this little expression right here from Ohm's law. Vir, or I is equal to V over R. And again, we're going to touch questions where we talk about these things. So I'm just kind of quickly going through. So let's see now, Alright, so we need to know Ohm's law. We also need to know about electrical safety. Alright, so electrical safety, and that will stem from electricity in the home. Right, so we need to know about electricity in the home. So we need to know that electricity is supplied to our homes in the form of AC. Right, so alternating current is what we get at home. Alternating current is what we get at home. Also need to know that it is connected in parallel. And as I talk about this, I kind of skip over something. We need to know about series and parallel circuits as well. So the electricity in our homes is connected in parallel. We also need to know about the color code for the wires. So the international color code. So I'm going to just touch on that here. So the international color code for insulators. So we use blue for neutral. We use brown for live, and we use green or yellow for the ground. Alright? So, you need to know these things. And again, don't worry about this so much in terms of how quickly I'm going through. I'm just kind of, showing you what you guys should be aware of. So as you're studying, you want to make sure that, okay, you check on these things. And as I said, we're going to be looking at some questions shortly. Next thing that we need to be aware of now is we also need to know about safety. Alright, so we need to know about the use of the fuses, circuit breakers, and we need to know about this thing right here, the ground wire.
Sir,
Yes?
in the recording class?
Yes, I am recording. It's recording. Alright? So we need to know about safety, the use of fuses, the purpose of fuses, why they are used, circuit breakers, and the purpose of the ground wire. We also need to know about electrical energy consumption, right? Electrical. So let me just say electric bill. So you need to know about the electric bill, and you need to be able to apply the formula where we say that the electrical energy, E, is equal to the power in kilowatts multiplied by the time in hours. So E is the energy in kilowatt hour, P is power in kilowatts, and T is the time in hours. Alright, so that's pretty much it that we should be aware of. So with all that said now, I think we can attempt a question. We have been talking for some time, so let's see if we can attempt a question, and we're going to see how many of these things come out in that question. So let me see if I can load up a question. Let me see how I can do that. Alright, usually this thing kind of creates a little problem when I try to load questions in. But let me just try in the meantime. And while I'm waiting for the question to be loaded in, any questions that persons have, any discussions that we can have, we can do that right now. So, any questions? Questions?
No, sir.
Oh, we must have questions, man. Make up a question. Something. Let's get a question.
Wait, just make up a question.
Yeah, in terms of like what we just talked about a while ago. Like maybe I said something that don't make no sense and you want to know what it is about.
Oh yeah, actually, sir. Why would you know about the bill, the light bill?
Yes, because your syllabus, when we look at electricity in the home, right, your syllabus want you to talk about, want you to be aware of how energy can be conserved in the home, and they want you to just be familiar with, okay, how the electric bill is calculated. So you can actually...
So basically, conservation and usage of light.
Yes. Because what they want you to see now is that based on the device, right, and its power rating, and how long you use it, that will determine how much the electric company will charge you. So they want you to be aware of that.
Okay.
Yes, and for some reason I have a feeling, and it's something that I don't try to do, to try to predict the paper, but I kind of have a feeling that they're going to test you this year on something related to energy and energy conservation, because you can remember a couple years ago, or maybe a couple months ago, when there was, the war break out in Ukraine, and gas prices start to raise up and all that. And persons struggling with the light bill, and struggling with things like gas price, taxi man complaining, motorists complaining about gas price. So I just have a feeling that they will somehow test you on that, and also know which will now lead to looking at things like alternative sources of energy. So I think they might test your knowledge on those things. So you just want to be aware of that as you are doing your preparation, and think of how you can actually express yourself where that is concerned. All right, so I think we have a question here, so let's jump into that. Let me just get this thing to get ready. And in the meantime, any other question about the exam, about anything related to as we prepare for the exam? Any questions? Anything? Samuels? Anything? Mullins?
Sir.
Yes, Mullins?
Sir, for the circuits within series and parallel, they would give us a draw instead of giving us a diagram, or we just do it to illustrate the answer.
Alright, say that again.
So for the circuits where we're drawing them in series and in parallel, would we have to, like, they give us a question when we would draw the circuit instead of like them giving us a diagram?
Okay. When I check past papers, I don't see they give you frequently. I don't see them give you many opportunities to draw this. Well, yes, they can, because as a matter of fact, I'm thinking they actually, one time I remember there was a question where they asked you to draw. So they gave you 3 resistors and they said, okay, draw a circuit to show the resistors in series and then in parallel, and they said, okay, calculate the resistance in series and calculate the resistance in parallel. So it's possible they can give you a question like that. So you want to be able to know how to draw a simple series circuit or a parallel circuit. So I see like persons get knocked off. So Michael Shea,
Yes, sir.
are you good? Good with this so far?
Yes, sir.
Alright, so let's go. I know the others hopefully they'll be able to join back shortly. So the first thing it says here, we're to explain what is meant by electrical resistance. So I always tell persons, in physics, we tend to give these things in physics names that are actually meaningful. Because when we think of resistance, right, it just simply means that, we're opposing something, not true?
Yes, sir.
Right? And if we're talking about electrical resistance, it's basically the same thing. We're opposing electricity, right? And electricity is merely the movement of charges. So when we talk about electrical resistance now, we can talk about electrical resistance in terms of a property, right? A property. So we can have an electrical device that resists the flow of electric current, and we can refer to that as an electrical resistor because it offers electrical resistance to the circuit. So we can say that electrical resistance, we can just simply say that this is alright, I think I need to see how I can close out some of these things. In the meantime, Jardine, what would you say is electrical resistance?
So substance's ability to resist the flow of electrons.
Okay, okay, right. Along those lines. So you said that it's the ability to resist the flow of electricity. Yes, yes. We could look at it that way, right? Now, to put that together, now we can merely say that this is the this thing kind of giving some problem now, you know. It's giving some problem now. It's kind of giving some problem now with the because I have a lot of these things open, and I should probably close out some of them just to make this thing a little more faster or whatever. Alright, so alright, so let's see this. Alright, so we can relate, as I said, electrical resistance to some property. So we can say that this is the property of a material, right? Which again, there's a log, which resists the flow of electric current, right? Or charged particles. So which resist, or let's say, you know, it I don't want to use the word resist again, so we could say that it opposes, let's say that word, opposes, I think it's 2p in opposes the flow of electricity, right? And we could, you know, add to this that and electrical resistance is measured in ohms, right, which is OHMS. That's a symbol for it. So on the exam, you want to express yourself to the examiner, let them know that, okay, you know what you're talking about and you know how to express it clearly. So that's that. What do you have that? We have that so far?
Yes, sir.
All right. So next thing now says that the circuit shown in figure 1 shows the interconnection between electrical devices B, C, and a voltage source A. So here we have a circuit. Now the first thing that we need to do is to identify the type of connection employed. So I should have mentioned series and parallel circuits, but it allows us to talk about it here now. So it says we're to identify the type of connection employed. So this is our voltage source. So we're going to have electric current, flowing from this source right here. So we're going to have electric current. Let us say we consider electric current flowing here. So this is the current flowing. Now when the current flows along this wire, when the current reaches right here, what will happen to the current? What will happen to the current? Huh? Changes direction. Okay. What do you say, Micah Shea?
Sir, you say same thing, change direction.
Change direction, all right. So let's consider it this way now. Let us say we have, let's just imagine for a second that, you know, we have a water pipe, right? Let's say we have the water pipe right here. Let us say, let me just do it right here. So this is a water pipe, and let's say it goes something like that. Right, so this is the water pipe. Now the water is flowing down this pipe, and it reaches a section right here. What will happen to the water? Let's say I label these channels A and B. What will happen to the water?
Some will go over A and some will go over B.
So some going to go this way, some going to go this way. So when we look at this circuit right here, same thing will happen. So when the current is flowing, once it reaches right here, because it has two pathways, some current flows here and some flows there. Now once we have a circuit in which the current has multiple pathways, then we're talking about a parallel circuit. Right? So a parallel circuit has multiple multiple pathways for current. So once we have multiple pathways, just as what we see right here, so when the current reaches here, it can flow along this path and go through B, or it can continue here and go through C. So we see that we have two pathways for the current to flow. So means then that we have a parallel circuit. On the contrary, if we talk about now a series circuit, we're going to see that if the parallel circuit has multiple pathways, the series circuit will have what could we guess and say? Brittany?
Flows in one direction.
Repeat for me.
It flows in one direction.
Flows in one direction. I would be a little more careful with that, by saying direction, but more so pathways, right? I would more so say pathways or pathways. So in this case, with the series circuit, it will have a single path for the current to flow. So when you're looking at your circuit, you always want to look at the path that the current will take. So with the parallel circuit, the current will have multiple pathways. So what it means now is that these devices are connected in parallel type of connection. So we could say now that we are using a parallel connection. Okay? So this would represent a parallel connection. So B and C are connected parallel to each other. Okay? Good?
Yes, sir.
Alright, so next one now says that we're to give the meaning of the circuit symbols labeled. So B. What is B? What know what is B?
A resistor, sir.
A resistor. If you're just starting out physics and you say, okay, it's a resistor, could I give you a mark for that? Because anything connected to a circuit is a resistor effectively. However, this is specially designed to carry out a particular function in a circuit. Now, this device right here is a motor, right? A motor. We did not talk about it earlier in our discussion, but this is a motor. But C now, we should know C. What is C? But remember?
Lamp.
Huh?
A lamp.
A lamp, right? So we could say is a filament lamp. Right? So that's a filament lamp. Now, they say now here, we're to name the type of voltage produced at A. So, what type of voltage would you expect to be produced at A?
Alternating current.
Right? Alternating current, or we could just simply say an alternating voltage. Now, the reason why we say alternating voltage is just by the symbol. Alternating voltage. So just by the symbol, notice if you look at this now, you see that little sinusoidal waveform, right, like that, just like what we drew earlier when we were talking about the alternating current. So we see that symbol, that sinusoidal symbol again. So once we see this, we must think about alternating current, right, or alternating voltage. Okay. Are we okay with that? Yes, sir.
Yes, sir.
Okay. All right. So there's a follow-up to this. Let me see if I can load up the follow-up question. So this one. All right. So based on what we just talked about a while ago, any questions? Any questions you may have? And also, as I'm going through, are you guys taking down the information and not just watch along?
Yes, sir.
Okay, good. So let's see now. All right, so let's see the follow-up to that now, to those questions. All right, so next it says now that a fluorescent lamp is rated at 15 watts and runs on 120 volts. So what they're telling us right here, they're telling us the power rating. So this is the power rating of the lamp. This is the power rating, and this right here is the potential difference or the voltage. Right? Potential difference, voltage. You know, we can get away with talking about them loosely. Now they say we need to calculate the current which the lamp draws from the main supply. So here we see we have the power, we're given the voltage, and they want us to find the current. Now if we go back up now to the list of things that we talked about, remember we talk about power somewhere. So we talk about power right here. And we talk about these three different formulas. P is equal to IV, P is equal to I squared R, or P is equal to V squared over R. Now in this case now, they gave us the power, so they gave us P, and they gave us V, and they're asking us to find I. So we can use this formula right here. So, as I said before, these are the things that, you know, the questions will now call on you now to be able to recall and then now apply the knowledge. So that is why, you know, I kind of went through these quickly to just kind of just let you know, okay, what the syllabus can ask you to be aware of, and then you're going to just simply apply the principles. All right, so we can write our formula. So we can say that the power P is equal to what? Power.
15 watts.
Huh? Well, the formula. Let's write the formula first.
Oh. IV.
Right, so power is equal to IV. Now, once we have our formula right here, we want to find the current. So we can do some transposing. So that's your application now, how you are able to transpose. So since you want to make I the subject, we can divide this one by V. So V cancels V, leaving I. But if we divide one side by V, we also have to divide this side by V. So then, we get I is equal to P over V. Now, in the question now, we're given some information. So we're given the power, P as 15 watts, so we can say 15 watts, and the voltage is 120 volts. So then, doing that division, what do we get? Something with 9 in it, 0.9 or something. Is that 0.9?
0.1.
Okay, 0.1 something, 0.1 what?
25.
Oh, 0.125. Alright, so let me write that down. Alright. Sorry, I'm trying to open up this calculator. So everybody got the 0.125? Alright, so that's I'm trying to open up my calculator, but it's kind of not working out for me. But anyways, so this is 0.125, and don't forget the unit. What's the unit?
So amperes.
Amperes, right? 0.125 amperes, right? So that would be our answer right there. Next thing now, it says we're to calculate the resistance. So calculate the resistance when the lamp is lit. So now, they want us to find this thing called resistance, right? So they want us to find resistance right here. So once they say we should find resistance, we can somehow think about Ohm's law. Right? 1 second. We can somehow think about Ohm's law because Ohm's law deals with resistance. Hold on a second. How is this? Hold on a second. This thing. Give me a second. Because I have a never-ending pop-up. Sorry about that. Alright, just bear with me a little bit. Computer kinda acting up a little bit. Alright, so in the meantime, let's see if we can figure out a way with this question now. So we still want to find the resistance, right? How would we go about finding the resistance in this case? Anything we can do to find the resistance? Oh, my audio is muted. Alright, yes. Anything we can do to find the resistance?
So you would divide power by current. Current squared.
Okay. Divide power by the current squared. Okay. Cool. Yes, you could do that. Now, I just want to share something with you, right? As an exam tip. Right? So we're saying, because we know, in fact, we have this formula right here that says that power is equal to I squared R. So we can find the resistance by dividing the power by the current squared. So we can use P is equal to I squared R, make R the subject where we get R is equal to P over I squared. Now, this I right here represents the current, not true?
It's true.
Right? Now, what if for some reason we calculated the wrong current? Right? If for some reason we calculated the wrong current right here, might cause a problem here. Right? So, in this case now, notice that we're given the voltage, right? Well, as a matter of fact, you know, I mean, either way we take it, I mean, we still have to use the current, really and truly. We still have to use the current. Still have to use the current, right? So, okay, right? Yeah, still have to use the current. So, in this case now, I mean, it wouldn't matter in this case because we still have to use the current. But in some cases now, you can choose, so let us say that, you know, there was another way we could find the resistance, right, without having to use this current. Now you could use that method so that if it is that this value is incorrect, it doesn't affect your answer going forward. But in this case now, I mean, we have to use the current regardless. So R now is going to equal to the power, which is 15 watts, divided by I squared, so that's 0.125 amperes, and we square that. So remember to square it when you're doing the calculating. So we're going to get 15 watts divided by 0.125 squared. What's that? 0.125, so 1 over 8 squared, that's what? 1 over 16, so that's 0 something, 0.325 or something like that. What do you get for that? 0.125 squared is what? Anybody work it out? Huh? Nobody hearing me?
Sir, the whole thing you asked for?
Well, I mean, you could work it out in one go, right? If you're comfortable. So when you work this out in one go, but you know, just to be safe, I like to do it step by step, especially, you know, when you don't want to compromise your answer. So when we square that, we get 0.016, rounded up to two significant figures. So then now we can say now 15 divided by 0.016, and we get a value of 937, or approximately 940 ohms. Alright? Cool?
Yes, sir.
Okay. Alright, so 940 ohms. Alright, so, and you could go ahead and just plug this into the calculator directly and get an answer. But once you show you're working, the examiner will award you the marks accordingly. That is why, you know, it's important for you to show working as you're doing these questions. So now, next thing now, they say we need to, when the lamp is lit, 4 watts of energy supplied is lost as heat. Calculate the efficiency of the lamp. So now, for this question now, they're looking into a different thing now. So now they're talking about efficiency. So now, they say when the lamp is lit, 4 watts is lost as heat. Now, when we talk about efficiency, we're talking about how much input power or energy, so input power or energy is converted to useful power or energy. That's really what efficiency deals with. So how can we approach this thing now? How could we approach this question?
There E equal P times T.
E is equal to P times T. Alright. So let's see now. So let's jot down what we're thinking. So E is equal to P times T. Okay? So what's next?
So we have energy in this case, right?
Well, do we have energy? Do we have energy?
No, say never give me no.
But what do we have?
Power.
Power, right? So again, looking back at what we say about efficiency. Efficiency tells us how much input power or energy. So in this case, we can talk about the power. How much input power is converted to useful output power. Right? Now we're talking about a lamp right here. Talking about a lamp. What's the purpose of a lamp?
To show light.
To show light, right? But how are we going to show that light?
So basically anything converted into heat, then that energy now electricity go up in a little box and light.
Okay, so you know, to summarize that, a light bulb is responsible for taking electrical energy and convert it to light, right?
Yes, sir.
But if you go and you touch your light bulb when it is on, yes it is giving you light, but if you touch the light bulb, it's going to feel how? Hot, right? It's going to feel hot, right? So even though the light bulb is built to give you light, it's giving you some heat, but you don't want the heat from the light bulb. If you want some heat, you can probably get a iron or a
Fire.
thing, right, or a stove, you know. You could use that for heat. You don't want the light from, you don't want heat from a light bulb, you just want light. So what we're saying now is that that heat that is produced, it is not useful. So we consider that as wasted power, okay, or wasted energy, typically, right? So now what they're saying to us now is that 4 watts of power is lost as heat. Now, again, the light bulb, its responsibility is to say, okay, give me some energy, electrical energy, and I will give you some light. But because of, you know, the properties of the bulb, it's going to give you some heat as well. So now, what we need to now be aware of now is that, okay, since we have 4 watts of power being lost as heat, essentially what this is saying is that, because remember, you know, that the watt is the unit of power, and power is how much energy is converted per second. So what this is saying is that we have 4 joules of energy being lost as heat every second. That makes sense?
Wait, what?
So, because remember, the watt is the SI unit of power, and power is energy over time. So when we're talking about power, it is how much joules of energy is being converted every second. So we can write the watt as the joule per second. So what this is saying is that if 4 watts of energy, 4 watts of energy, 4 watts of the energy supplied is lost as heat, what they're saying is that 4 joules of energy is being lost to heat every second. That's really what they're saying, okay? Cool? Are we good with that?
Yes, sir.
Alright, so now, again, how much input power is converted to useful output power? So consider in this case that 4 watts of power is being lost. So now, we need to know, okay, how much power did we input into the light bulb? Anybody know?
15 watts, sir.
15 watts. How we know it's 15 watts? I wonder if they're going to bulb we plug in. How we know?
Because they gave us in the question.
Right, they're going to give us the information. So we always want to be looking out for these information. So see it right here. This is the power rating. So the lamp operates at 15 watts, right? So when we give it 15 watts of power, it's going to operate efficiently, or not efficiently, but it's going to operate effectively. Let me use that term, right? So 15 watts, we give it 15 watts, right? But 4 watts is lost as heat. So then, what we can say now is that our input power is equal to the 15 watts. And the output power now, which is how much of the input power we get to useful power. So let's say useful output power. So again, 4 watts of power is lost as heat. So if we supply 15 watts of power, we expect to get 15 back out as light. But 4 watts is converted to heat. So how much will be converted to light? 11, right? So we just say the 15 watts, which we supply, minus how much is lost. Sorry, this is 5. 5, this is not 4. This is 4 right here. So 4 watts. Then now we get 11 watts. So now to calculate the efficiency now, we use a formula. So we say that efficiency, it is always expressed as a percentage. Efficiency as a percentage is equal to the output power, or you could use energy, but in this case, let's use power. Output power over the input power multiplied by 100%. So then, so all of this, you know, is application, right? All of this is application. right? And the use of knowledge. So we want to be able to relate, first of all, recall the content, and then now based on the question now, we apply the knowledge, right? So that is where now we use of knowledge. So output power now we say was 11 watts divided by input power, which is 15 watts, multiplied by 100%. So then, from that now, 11 over 15, so we say 11 divided by 15, we get like 0.73, and we multiply that by 100%, so we're going to get roughly 73.3%. So it means that the lamp is 73% efficient. So 73% of whatever energy or power you give to it will be converted to useful power. Alright? Now one thing we need to know about efficiency, if you work out efficiency and you get a value greater than 100%, something is wrong. Because you cannot have efficiency being greater than 100%. Alright?
Yes, sir.
So that's pretty much it. We have any questions?
So what if they like gear the efficiency to find one of the two days?
Okay, same process. So let us say that they say, okay, the efficiency is 80%. So if they say the efficiency is 80%, and they say, okay, this is the input power, and they say, okay, how much power, how much of the input power will be converted to useful output power? So you're using the same formula right here. So you have the efficiency as a percentage. Let me do it right here. See if I can squeeze, like, do it right here. So this is 80%, right? The output power is what we're trying to find. So let us say this is P, output power, right? And we know the input power as 15, right? So what we'll do now is that, remember that 80% is, as a fraction, is just simply 80 over 100, right? 80% as a fraction is just 80 over 100. So what we'll do now, we'll just simply say 80 times 15 divided by 100, or for simplicity, we just multiply 15 by 0.8. And I think I get 7.5. No, I don't know. What you get for this? You can't get 7.5. Like 12 or something? What do you get for this? What you get when you work this out?
12, sir.
Yeah, 12, yeah, something like that, right? 12 watts. Alright? So that's that. Alright? Question? Okay. Alright, so let's see if we can try something else under electricity. So let me see if I can load up another question. So as I said, I mean, these things that we talked about earlier, we see they coming into play as we look at these questions. And that's what the examiner will be testing you on. So you want to just make sure, say, you can talk to the examiner when he's asking you these questions. All right, so let's see which one. Let's see. All right, yeah, let's try this one, because this one always kind of create a problem to students. So let's talk about this one. Lorena, any question for me? Anything? Any question?
No, sir.
Okay. All right. So let's look at this thing now. All right. So this is the first part. I'm going to load the second part after. So let's start with this. All right. So it says we're to complete table 3, which relates electrical circuit symbols to the names of electrical components. All right, so first one, first symbol, what's that? What's the first symbol?
Cell.
Cell, right? So this is a cell. Now, they want us to draw a variable resistor. Now, we know that the symbol for a resistor is this one right here. But if we want to make a variable resistor, draw the symbol for a variable resistor. What do we do? Huh? Here. Jaden?
Sorry, the draw arrow through it.
Right, so let's put an arrow through it like that.
Arrow.
Yes, yes. So we put the arrow through it to indicate that it's a variable resistor. For this symbol now, what's this? Right, so a filament lamp. Right, and then for this one now, this one is what's this? Alright, Michael Shea, what's this? Yeah, no, but Michael Shea know it.
So I think I accelerate something, current something. Remember.
But we just talk about Michael Shea, right?
Sir, let me say, sir, accelerate AC, sir.
Right, AC. Right, AC source, right? So this is the alternating current source. So because of this symbol right there, right, alternating current, which you know, go like that, you know. All right, so semiconductor diode now. Triangle. That's it? Line through it, like that?
Line get back.
Right, so line like that,
Only a circle.
No, circle, that talk about, we call them thing again now, logic gate now. Not gate, you talk about. Right? So that's the NOT gate. We have the triangle like that. That's the NOT gate. Right? So that's the semiconductor diode. And then
a fuse?
Yes, this is the fuse. Right? So those are our symbols. Now, here's our circuit now. So, let's say we have this circuit right here. So let's read what they say now. So when we're looking at these questions, you know, I mean, you always want to read what they're telling you and then look at the circuit to say, okay, is it true them talk? So they say, in the circuit in figure 2, this is figure 2, R1 is equal to 4 ohms. So you check to see, okay, R1 is 4 ohms. So you say, all right, good. They say now R3 is 8 ohms. So you look to see R3 is 8 ohms. And they say that the supply is 2 volts. So you look up and you see, oh, sorry, not 2 volts, 24 volts. So you look and you see, okay, 24 volts right there. Then now they say, okay, with the switch S open. So you look and see, okay, this is switch S, it is open. The current I through the ammeter is 2 amperes. So you look and see, okay, yes, that is so. So what they're telling you is basically describing what's happening right here. So now, from there now, you can now be able to apply or approach the question. So the first thing they say we need to do is to state the formula which relates voltage, current, and resistance. So what's that formula?
So I
Equals I times R.
Right? So V is equal to IR, right? Which is Ohm's law. Right? So V is equal to IR from Ohm's law. Right? So V is the voltage, I is the current, and R is the resistance. Now, oh, I need to load up the other part. So that's pretty much that so far. So let me load in the next part of the question. And as we wait, any questions? Any questions?
No, sir.
Alright. So I think this is the next part. Alright, so let's go 60. And again, Lorena, any question? Lorena still on? Lorena, any question? Huh?
Oh, no. No, sir.
Okay. Alright, so next thing now, let's say we're to calculate the value of R2. So they want us to find the value of R2. So let's look back at the circuit. So this is our circuit right here. So what's the approach we're going to take now to find the value of R2? Because first of all, this is R2 right here. Right, R2, let me see if I can highlight it. So this is R2 right here. So what approach can we take to find the value of R2?
Sir?
Yes?
Oh, come on.
What can we do to find the value of R2? Any suggestion?
Sir, wait. No say answer it, sir.
Brittany, how can we find R2?
Sir,
Yes, read, go ahead.
sir, may I divide the current by voltage and then subtract R1 from it.
Okay.
And go get
Okay.
what sure is that? Sir, we're probably not sure enough. Yes,
Alright.
probably right.
Alright, so let's talk about it now. Green, I see you raise your hand.
Yes, so I was thinking that you could like find how much current go through R1 and then let's go to R3 if you can. Get off you take away that R2 from you again.
Alright. Alright, hold on a second, Jaden. Michael Shea. Let me not ask Michael Shea. Jordan.
Yes, sir.
Yes, how much current is flowing through R3? Huh? No, that's the resistance. How much current is flowing through R3? Huh? 8 ohms. Alright, we're gonna come back. We're gonna come back. Huh?
Say about say about 12 volts, sir.
12 volts. Alright, we're gonna come back to that. Jaden, you were saying something earlier.
Sir, no.
Alright?
Sir, wait, our combination circuit is
Yes, well. Hold on. Don't want to give away that as yet. But hold on. Let's do some analysis. Like just like looking at the circuit basically. So this is what we have. So we have our circuit right here. Now let's just focus on this switch right here. This switch S, it is the examiner tell us that the switch is open, right? Yes? Somebody say yes, no, if I so.
Yes, sir.
Right? So the switch is open. So with this switch open, what we're going to see is that no current will flow through this resistor R3 when this switch is open. So the current flowing through R3 is 0. So all of the current is flowing this way. So the current goes like this, goes through this resistor, continues around, through R2, and go straight around. So what we see now is that the current is traveling on a single path. So once current flows along a single path, we know that we have a series circuit. See that, Jaden?
yes, sir. I
Right.
current go constant, sir.
Right, the current will be constant, right?
In a series.
In a series, right? So the same current flowing through R1 and R2 in this configuration with this switch right here open. So then, what we can do now is we can now find the total resistance of the circuit, because we have these two resistors, R1 and R2. But by the way, before we even get to that, we have these two resistors, R1 and R2, and we said that they are in a series circuit. For resistance in series, the total resistance is equal to R1 plus R2. That's the total resistance. So the total resistance is the sum of R1 and R2, but we don't know what R2 is, right? So we can't find R2 with this equation. However, we can use Ohm's law, which we talk about up here. Where is it? We talk about it somewhere. Oh, right here. Ohm's law. We can consider V is equal to I times R. So then, we can make R the subject. Divide by I is cancelled. Divide by I right there. So R then now is going to equal to V over I. So then, we say V is this value right here, because they gave us this value, 24 volts. See there right there again, 24 volts divided by I, which is 2 amperes, because as I said, Jaden, the same current will flow throughout the entire circuit. And the current flowing in the circuit is a 2 amps right here, which is being measured by this ammeter. So 2 amperes. So we get that divided by that gives us what? 12 ohms. So that's the total resistance. So then, what we're now saying is that the total resistance, which is 12 ohms, is equal to R1, which is 4 ohms, plus R2, which is R2. We don't know it. So then, basic math, R2 is equal to 12 minus 4, which, as I mentioned, Jaden, based on your explanation, would give us 8 ohms. That makes sense?
Sir,
Yes.
isn't this a way easier, one way easier or another way, sir?
No?
Sir, it's a series circuit, right, sir? And the same current to pass through, you see R resistors on the series, sir. That
Yes.
means since R is 4, wouldn't R is double that?
No. No, you can't make them guess them. You can't make those guesses. Right? I mean, you could, you know, let me see now. You know, you could try this way. You could try this way. You could say, all right. You could say, all right. But it's probably a same double step, because you're going to say, all right. If this is 2 amperes, you could say V is equal to IR. So the potential difference across this is going to be I, which is 2 times the 4, which is 2 times 4 is what, 8? That's all, yeah, 8 volts. That's right? Yeah, 2 times, no, yeah, 2 times 4 is 8, yeah, my bad. So 8 volts right here, right? No, the thing is, it's just the numbers, like I'm seeing the 4 right here, so I'm wondering if it's supposed to be 4 times 4, you know? That's why sometimes, you know, you have to show the working. So, alright, so this is 8 volts. So if you notice, alright, it's a series circuit, 8 volts across here, that means the remainder are going to drop across right here. So if this is 8, and you have a 24 volt supply, this is going to be 16 volts, right? Then now we can say, okay, if this is 16 volts, we can say, you know, R is equal to V over I. So V is 16, and I is 2, so you get back 8 ohms right there. So you could do it that way there, but I don't see it being any easier, you know? Because a lot more concepts to consider in this approach, right? So it's another way you could work it. Alright, so that would be for that part. We okay with that, by the way?
Yes, sir.
Alright. So I'm not hearing from Mike and the others. Everybody good? Like, don't let just one person say them good.
Yes, sir.
Alright, cool. Alright, so that's that. Next one now says, what is the reading on the voltmeter? We just did that a while ago, but let's just kind of analyze it now. So we want to know the reading on the voltmeter. So we know the current flowing through this resistor, which is a 2 amperes, right? We know the resistance, we just calculated it right here. So then we can say V is equal to I times R. So I is a 2 amperes flowing through the resistor, and the resistance of the resistor is 8 ohms. So 2 times 8 gives you 16, which is what we kind of work out right there. So that's 16 volts. So it's just applying Ohm's law and what we know about the series circuit to solve this thus far. When you guys are ready, let me know.
Yep.
Move. Can move now?
Oh, yes, sir.
All right. So that's that. And again, any questions before we move on to the next part? Mullins, any question?
Sir, I2 or I3 would be parallel, right, sir?
Well, no, you know, the switch is open, right? Unless you're going to tell me that, okay, you close the switch, right? If you close the switch now, that is when they're going to be parallel, because no current flows through this switch right here when it is open. All the current goes here, okay, through R2, okay?
Yes, sir.
All right. So next thing now, it says if switch S1 is closed. So now we close the switch. So S1 is closed. Sorry, S is closed. What is the new reading on the ammeter? So they want us to find the current. All right. So to find the current, we will say, let's say we first say I is equal to V over R. Because we know that from Ohm's law. So I is equal to V over R. So we start with that. Now, if we're saying I is equal to V over R, we need to know the voltage of the source. So we need to know V. V is 24, from what we can remember. R now is the total resistance of the circuit. So what we're saying now is that, okay, we close this switch right here. So we close the switch. So we want to know what is the total resistance. So now, what we're going to see now, as you mentioned earlier, Jordan, R2 and R3 will now be in parallel when this switch is closed. So we have these two resistors in parallel, and we have this one in series with those two resistors that were in parallel. So right now we see that we have a combination circuit or a series parallel circuit. Okay? Yes?
Yes, sir.
Now once you have a series parallel circuit, you have to work out one of the combination first, right? Either you work the series combination or you work the parallel combination. In this case, we can choose to work out the parallel part. So we can choose to work out the parallel part. So we have two resistors in parallel. So we can say, if we have two resistors in parallel, we can say that the total resistance or the equivalent resistance, let's just say the equivalent resistance, since we're not finding the total as yet, the equivalent resistance for two resistors in parallel is always their product over their sum once you have two resistors in parallel. So the product now would be 8 and 8, and you're going to see something that, okay, you're going to see something with this, and I'm going to mention it shortly. So we have 8 times 8 divided by 8 plus 8. So now, 8 times 8, I'm going to give you, I think, 64. And 8 plus 8 going to give you like 16. So 64 divided by 16 gives you what? Huh?
4.
4, right? So this is 4 ohms. So what we're saying now is that these two resistors in parallel, they supply or they provide an equivalent resistance of 4 ohms. So we could just take out those two resistors and just replace it with one single resistor that has a resistance of 4 ohms, right? Then we see now that we now simply have a simple series circuit. So we have a 4 ohm resistor right here, and we have an effective resistance of 4 ohms here as well. So once resistors are in series, just as what we say right here, we just add the individual resistance. So the total resistance then now, RT, is just going to be 4 ohms plus 4 ohms, which works out to be 8 ohms. So then, the current I then now is equal to V over R, where V is 24 volts and R is 8 ohms. And this works out to be what now? Me 3 this, yeah, 3 amperes, right? Is that beautiful?
Yes, sir.
Okay.
Sir,
Yes.
to find R equivalent, then I say like I can use 1 over R1 plus 1 over R.
Yeah, man. But I'm just giving you a shortcut way. This is when you have only when you have
But
two
sir,
resistors. Huh?
I'm going to get on different answers.
Alright, so 1 over R EQ is equal to 1 over R1 plus 1 over R2. And I'm just using R1 and R2 arbitrarily. What value you get, by the way? What value you get? Jaden, what value you get?
Sir, I'm going to get... Wait, I'm probably... Wait, I'm going to get 0.5 for some reason.
0.5 for some reason. It's 0.5. Let me see now. I think I know why you get the 0.5. Let me show you why you get the 0.5. For this case, you didn't necessarily have to find an LCM right here, so. Did you find an LCM when you were working it out?
So let me just use 8.
Just use
8.
decimal?
No, 8.
Oh, just use 8, okay.
That's what you
But what
got.
I'm saying is
8.
that because the denominator is the same, you don't need to find LCM. You only find LCM when the denominators are different. So you could just add across. So 1 plus 1 gives you 2, and the denominator remains the same. So I think what you did was you divided 2 by 8, and that's why you got that value. But what you should have done, 0.5, no, let me see. Yeah, we're going to get 0.5 for that. What you should have done is consider that this is 1 over REQ. That is equal to 2 over 8. So to find REQ now, you have to invert. So you flip this one, and you get REQ over 1 is equal to 8 over 2. Divide that out, that's where you get the 4. Okay? 2 divided by 8, you're going to get 1 over 4, you're going to get a quarter, 0.25. So, did you do the inverting part right here, the reciprocating?
Yes, sir. That's what I'm going to find fast, sir.
Right.
Don't put the 8. I'm find the LCM.
Okay.
8. And then, it's 8 and 8 1 time. Oh! Sir, you know what I'm saying? So 8 went to 8. 8 times and then times the 1 by the 8.
Oh.
Alright, sir.
Alright. But as I said, once you have just 2 resistors in parallel, you can use the product over sum. Right? Only when you have 2 resistors. Alright, so that's pretty much it. I believe we would have touched on, only thing we haven't touched on is electrostatics. But we start to touch on most of these things. We did not look at Q equal IT and those things. But let's now talk about electromagnetism. Right? Let's look at electromagnetism and see if we can find some question on that. So electromagnetism. And if you guys have any question on these electromagnetism thing, because I'm thinking where we can find questions on this. I have questions but it's just to find them. So alright. So with electromagnetism and also magnetism in general, let me say magnetism and electromagnetism. Magnetism and electromagnetism. So with magnetism, we need to know the magnetic field lines, or in other words, we call it again magnetic field. First of all, need to know about the magnetic field, which is just an area where a magnetic material experiences a force. So we need to know the magnetic field. Need to know about the magnetic field lines. Magnetic field lines. And some things about the magnetic field lines is that they always run from north to south, right? Always run from north to south, and they never intersect. Never intersect. So they never cross path, right? And we also need to know how to draw the magnetic field lines for a bar magnet. So this is a bar magnet like that. Need to know to be able to label one pole as a north pole and the other one as a south pole, right? So as I said, the magnetic field lines, they always run from north to south. So we can show that as going from north like that to south, and we show the arrow, use the arrow to show. So north to south like that, and again we have the arrow to show. And put another one, right? And we go from north to south, and notice that they never intersect, right? Never intersect. Now, as I draw this now, just remember another thing about the magnetic field lines is that they are strongest or concentrated at the poles. Let me just say concentrated at the poles. And as a result of them being concentrated at the poles, it means that the field is strongest at the poles. Concentrated at the poles. Alright, in the meantime, anybody finding any questions that we can look at? If you guys have any questions, you can send them in the chat, maybe as a PDF, and I can open it up and work through it. Alright, so that's that. We also need to know about the magnetic force. Need to know about the magnetic force. So we need to know that north to south attracts, right? Attracts. Need to know that north to north repels, and similarly south to south repel. So like poles will repel. So like poles repel, while unlike attract. Okay? Cool? Also need to know about magnetic materials. So magnetic materials. So magnetic materials, in other words, materials that can be used to form magnets. So some of these things include iron, steel, nickel, right? And different alloys, right? Certain alloys containing iron, right? Certain alloys containing iron, certain alloys containing alloy, ALLOY, right? Alloy is containing iron, right? Also need to know about the electromagnet, which we're going to talk about with electromagnetism. So let's look at that now. So we need to know about the electromagnet. Now, electromagnet is a temporary magnet. So electromagnet, which is a temporary magnet, right? And as the name suggests, electromagnet, it's a magnet that needs electricity. So once we cut off electricity, the magnet no longer is magneting, right? As what you guys will say, right? So, body okay so far? Right? So that's electromagnet. We also need to know of the different applications. So they are used in electric bells. Electric bells. Where else we use electromagnets, Jaden? We're still on. Where else we use it? Huh?
I remember.
Right? So we also use them in magnetic relays. Right? That's one of them, right? Jaden? They use in magnetic relays. They use them in speakers. Right? Speakers. Also another one, the security doors. I'm going to say security doors. Right? So yeah, we got a place in them of a buzzer in. It's an electromagnet that is operating that. Also now in terms of the junkyard, that crane, so I can say junkyard crane. Right? Junkyard crane. So they use it to pick up scraps of heavy metal like car parts and so on. So that's that. Now we also need to know about electromagnetism, or let's say electromagnetic induction. So we need to know about electromagnetic induction, right? So we need to know that one, a current carrying conductor right induces, or let's say no, I'm not say induces, produces a magnetic field around it. Right? So a current carrying conductor will produce a magnetic field around it. Now that magnetic field, let me see if I can draw something here. Do I want to do it slant? Let me just do it vertical. So we have a conductor right here carrying a current. So this is a wire carrying a current. Let's say this is the current going up like that. So this is a current I. Now this conductor carrying a current will produce a magnetic field. Now that magnetic field now will be in the form of concentric circles. So circles like that. So we're going to have concentric circles like that. Now the direction of these circles will be determined by the right hand grip rule. Alright? So the right hand grip rule. Anybody know about the right hand grip rule? Anybody know about the right hand grip rule? Alright, so what the right hand grip rule says is you take the conductor carrying the current and you're going to grip that conductor with your right hand. Now when you grip that conductor, you want to ensure, let me see if I can draw this, you want to ensure that your thumb is pointing in the direction of the current. So that's your thumb pointing up because the current is going up. And your fingers now, the direction of your fingers now will indicate the direction of the magnetic field. So let me see if I can draw this. I always have a problem drawing this. So something like that. Alright? Something like that. So if you grip the conductor with your thumb pointing up, since the current is going up, your fingers will curl in the direction of the magnetic field. So since your fingers are curling this way, based on how we grip the conductor, since your fingers are curling this way, what it means is that the current, sorry, not the current, my bad. Since your fingers are curled this way, what it simply means is that the magnetic field, the direction of the magnetic field is in this direction. You making sense? Repeat?
Yes, sir.
I don't hear you. Repeat?
Yes, sir.
Okay. That who are here, talk to me. Let me know if this thing making sense. I want this thing to be meaningful to everybody, so let me know. Michael Shea?
Yes, sir.
Okay. So that's the right hand grip rule. So now let's just, because what the examiner oftentimes do, they oftentimes give you diagrams looking like this. Let's say something like that. So this diagram right here indicates a conductor carrying a current into the page. So the current is going into the page. So if we use the right hand grip rule, we're going to imagine that, okay, we have the wire going into the page. So we're going to grip the conductor with the thumb pointing in the direction of the current. So since the current is going into the page, the thumb must point in. Guys with me?
Yes,
So what we're going to see now is that our fingers are going to form circles. Right? Let me just draw two. Fingers are going to form circles. Now, based on the curl of your fingers, since your fingers are curling, or you would describe your fingers curling? They're curling to the right or to the left? From your point of view. Fingers are curling to the right or to the left?
So to the right.
To the right, right? Because you're gonna place your fingers and so these will be your fingers kind of like that. And your thumb gonna go into the page like something like that. Alright, something like that you're going to see. Alright? So these are your fingers curling this way to the right. So therefore now, the feel is gonna go like that to the right, and then at the bottom, it's gonna go in the opposite direction. Okay? Now also now, they will give you this one with the dot, with the circle. And this one is when the current is coming out of page. So again, the right hand grip rule. And if into the page, the field lines are clockwise, this is going this way, so they are clockwise. For this one now, it's going to be anti-clockwise. And we can use the right hand grip rule just to prove it. So we're going to place the thumb so that it's pointing towards us. And we're going to see that our fingers are going to be curling to the left at the top and then to the right at the bottom. So we need to know these things, right? And we need to know that the magnetic field around a current carrying conductor, a straight current carrying conductor, is always in the form of concentric circles. By concentric circles we just simply mean, mathematicians, what do we mean by concentric circles? Mathematicians, what do we know? What do we mean by concentric circles?
Let me see. From what I remember, sir, there are special circles.
What's so special about them? What's so special about those circles?
Shape.
Shape, okay. Not only that, because all circles shape the same way. I believe all circles shape the same way, round, right? Oh boy, all circles shape the same way. Alright, so what we're saying now is that concentric circles just simply mean that they have the same center. Right? Same center. Concentric, so with the same center. I think it's Latin, right? But don't quote me on that. Alright, next thing we need to know now, we need to know about a solenoid. Solenoid. And we need to know the magnetic field around a solenoid. So now, for this one now, let's make a solenoid. So a solenoid is just, we take a wire and we loop it around. Right? Loop it around like that many times. Right? So that's a solenoid. Right? Now, if we consider that we have current flowing up on this side of the solenoid, So current is going up on this side. So the current is going to go up. It's going to go like this. It's going to flow to the front, then loop to the back, continue, continue, continue. What with me? Until it eventually leaves. So it's going to go out this side. Okay? That makes sense? Somebody talk to me. So the current is flowing. It's going to go down in the front, up in the back, down at the front, up in the back, down, right, like that. So I'm just using these to show the how the current is flowing in this solenoid. Alright? So what we're saying now is that when the current flows in a solenoid, right, we're going to get a magnetic field. Magnetic field similar to a bar magnet. Now we know that this is a bar magnet, and a bar magnet has a north pole and a south pole. So we're going to get a similar thing happening with the solenoid. Now for this one, we also use the right hand grip rule. But this right hand grip rule comes with a little twist, and we have to talk about the twist. So let me know when you're ready for us to talk about this. Let me know if you guys are ready.
Ready, sir.
Okay? Alright, so with the right hand grip rule for a solenoid, right? Remember, with the straight conductor, the thumb indicates the direction of the current, right? While these fingers indicate the field. Now, for this one now, the rules are reversed, right? The rules are reversed. So in this case now, the thumb, right? The rule of the thumb now is to tell you where the north pole is. And your other fingers now will tell you the direction of the current. Okay? So that's the difference with the right hand grip rule for a solenoid. So what they say now is that we have to place our right hand over the solenoid so that our fingers, right? Our fingers, our four fingers, so we could say four fingers, our four fingers are in the direction of the current. So what you see right here now, based on this diagram, the current is flowing down in the front. So then, we're going to take our right hand, and for the ladies, when you guys do your nails, you take your right hand and you curl your finger down to look at your nails. Right? That's what you do, right? Brittany? That's what you do? Talk to me. Who can talk? Who can talk? Just say that they cannot talk. So, talk to me, guys. Talk to me. I want to know if we're on the same page.
I wouldn't know about me.
Yeah, I know. Yeah. That's why I ask the females them, but them not cooperate. You know. But what we're saying is that in this case, because the current is coming down in the front, we're going to imagine that you're placing your hand over the solenoid so that your fingers are curling down in the front. So what you're going to see now is that it's like you have your palm open and you curl your finger down. That's basically what you're going to have. And what you're going to see now is that your thumb will be sticking out. Follow?
Yes, sir.
So your thumb will be sticking out. And what we say now is that the thumb indicates where the North Pole is. So where would the North Pole be on this diagram, on this solenoid?
To the right.
To the right. Because your thumb is pointing to the right, so this will be your North Pole. So the North Pole will be right here. And if this is the North Pole, automatically this would be the
South Pole.
South Pole. And remember, we said, what did I say? Wait. let's say about the field lines. The field lines, they always run from north to south. So we can show that. So we're going to have our field lines running from the north right here, going to the south, and it's going to continue through the solenoid, like that, right? And then one more now, from the north to the south, and continue through the solenoid like that. And the direction now is north to south like that, north to south. So that's how we determine the magnetic field around a solenoid. Any questions? Any questions?
So,
Yes.
What if you have like two of them put together?
Two solenoids put together. Yes. Okay. If you have two solenoids put together and you have a current flowing in one, and that is what we're going to talk about next, electromagnetic induction. So if you have one solenoid right here, let us say, and this is the basis, of a relay. No, not a relay, sorry, my bad. A transformer. This is the basic principle of a transformer. So we have two solenoid basically. Let me just draw a simple one. So one right here, and we have another one here. So let's say that this one is connected. Let us imagine that we're connected to this is more. All right, let me just, let's see. This is more, this is going to be more meaningful if we connect it to an AC source. Let me use an AC. So AC like that. So I connect it to an AC source. So this is an alternating voltage. All right, let me just, for simplicity, so we can understand the what's going to happen. Let me just use a DC so we can at least see that. Right? So we have our DC power right here. So current is going to flow from the positive terminal because we're considering conventional current flow. So current will flow here. So the current flows here, up, then it goes down right here, up at the back, down, up at the back, and then down again until it eventually leaves. So now, just like what we have right here, we're going to have our north pole right here, right? So when we just, let us say there's a switch in the circuit, when we just close the switch, we're going to have a north pole right here, right? We're going to have a north pole right here, and we're going to have the south pole. Now, as a result of this north pole being present right here, let us say this is connected to a little bulb, right? Let's say it's connected to a little bulb, right? And this is just context, right? This is just context. So we have a north pole right here. Now, this north pole, when we just turn on the switch, we're going to have a change in magnetic field. Now, that change in magnetic field now will induce a current inside the solenoid, right? Inside the secondary solenoid, which will now cause this light bulb to just glow for a very short period, right? However, if we want something meaningful, we simply replace this DC power with an AC power, and we're going to have that continual change in magnetic field, which will continue to induce a current in the secondary coil, which will give us current continually flowing in this light bulb. So that is the basic idea of a transformer, right? So that's really what's going to happen right here, right? So that's that. All right, so let's talk about something else now. So let's see now. So we'll talk about that. Let's talk about the motor effect. So we're going to look at electromagnetic induction shortly. But we have to talk about these things to get to there. So motor effect. Motor effect. Just checking in with everybody. How was today so far? Everybody comfortable?
Sure.
Yes. Mullins?
Yes, sir.
Alright. Akina, you were asking a question or you were just saying that you're comfortable with what we're talking about so far?
Just I'm saying it's okay so far.
Alright, cool. Mark O'Shea?
Yes, sir.
Are you okay with what we're talking about?
Yes, sir.
Alright. And Lorena?
Yes, sir.
You okay with what we're talking about?
Yes, sir.
Alright. Kind of going fast paced, you know, just to kind of touch these. But as I said, we're gonna see if we can find some questions. And if you guys find questions, you know, related to any of these things, then we can work them. So the motor effect. What the motor effect basically say is that when a current carrying conductor, current carrying conductor is placed in a magnetic field. So we place a current conductor in a magnetic field. What do you think will happen to it?
So like the current can interfere with the magnetic field.
Say that again?
The current is going to interfere with the magnetic field.
I don't hear. Repeat for me.
The current is going to interfere with the magnetic field.
Okay, and then what will happen?
And then it's like the field can disrupt or they can change voltage. Like that.
Okay. All right. So let's kind of look at this now. So, all right. So we are saying that we have a current carrying conductor, and we know from talking earlier, where is it? That a current carrying conductor produces a magnetic field, right?
Yes, sir.
Now we're talking about a current carrying conductor being placed in a magnetic field. Now that current carrying conductor will have a magnetic field associated with it, and we're placing that current carrying conductor with its magnetic field in another magnetic field. Now earlier I believe I mentioned something about magnetic field. It's an area where a magnetic material experiences a force. So if we have a current carrying conductor which has a magnetic field associated with it, and we place it in a already present magnetic field, no, it will not amplify it. What will happen is that, back to this again, you know, we said that a magnetic field is an area where a magnetic material experiences a force. So by placing that current carrying conductor in that already present magnetic field, it will experience a force. Okay? And that's the basis of the motor effect. That is why when you turn on your fan spins due to the motor effect, because we have current carrying conductors being present in a magnetic field in the motor of that fan. So that's the motor effect. Now, in simplicity, are the very basics. Let's look at the very basics of this thing. I want to draw a bar magnet. So let's draw a bar magnet. So let's say we have something like this. That, draw again. So we go like that, that, so, something like that. And then we have another one now, so we can make it look like this. What do I do next? So, right, something like that, right, like that, okay. So these are two bar magnets, right? We're gonna say this is north and this is south. So when we have these bar magnets right here, we're going to have a magnetic field associated with these bar magnets, and the magnetic field will be represented by magnetic field lines that will run from what?
North to south.
North to south, right?
North to south.
Easily. So north to south. So we're gonna say north to south like that. North to south, north to south, you know, something like that, right? Usually make them straight, but, you know, like that, north to south. So that's what we have. Now we're going to now take a conductor and ensure that it can carry a current. And let me use the ruler, because I might go over this several times. And you know, as I'm thinking about this, you know, I want to adjust this. Yes. So let's now draw our current carrying conductor. So this is the current carrying conductor. Right, so this is a conductor, right? And let's say it's carrying a current, right? Would you want the current to be going into the page, or you want it to go out of the page? Somebody select one. Into or out of? Into or out of? Into. Alright, so the current is the conductor is carrying the current into the page. So the current is going in this direction. So this is the direction of the current. And once we're talking about electromagnetism and we're talking about current flow, we always talk about conventional current, right? And conventional current is when we have positive charges moving, right? So conventional current is due to positive charges. So we have the positive charges flowing in, so we have a current flow going into the page. So now, to determine the force on this current carrying conductor, we will apply a thing called Fleming's left hand rule, right? And Fleming's left hand rule, sometimes, you know, you might hear a person say it's the motor rule. Motor rule. Right, so we apply the motor rule, which is for the left hand. So now, with the motor rule, and we would have, when we were talking about alpha particles in a magnetic field and so forth, and beta particles in a magnetic field, we were talking about the Fleming's left hand rule. So with the Fleming's left hand rule, we take our left hand, we're going to have our thumb like that, we're going to have our index finger going like that, this finger going like so, which is our second finger, and then the other fingers go like that, so you have your 5 fingers like that. So this is Fleming's left hand rule, right? This is the idea of Fleming's left hand rule. So with Fleming's left hand rule, you will have your 3 fingers, the thumb, your index finger, which we tend to call the first finger, use a different color, index finger, which is your first finger, and your second finger now, which is your middle finger. So we have the thumb, the first finger, and your second finger, right? Now, the thumb indicates the thrust, which is merely the force. So the thumb is what you're going to use to tell the force, right? Your first finger now will tell you the direction of the field, which is the magnetic field. And your second finger now will tell you the direction of the conventional current, right? So I'm going to say conventional current, which we say is the movement of positive charges. So now, let's all get our fingers, our 3 fingers at right angles. Right, so let's get our fingers at right angles. First 3 fingers, your thumb, index, and your middle finger must be at right angles. So can we get that? Guys know how to do it? So everything must be right angles. Huh? Guys able to do that?
Yes, sir.
Alright? So once you have your 3 fingers at right angles, what you'll do is you'll align your fingers in the direction of the field and the current. So basically now you're going to be setting your index finger and your middle finger. So your index finger is for the field, and the field goes from north to south. So your index finger must be pointing from north to south, in this case from left to right. the current is going in, the conventional current is going in, so your second finger must be pointing in. So what it means then now is that you're going to have to rotate your hand upside down. So if your hand is like this, you're going to have your thumb like that. This one is going to be going to the right, and this one is going to be pointing toward you. Alright, just imagine these are fingers nicely drawn. So this is your thumb going up, index going to be going to the right, and your middle finger will be pointing towards you. So in that orientation now, you're saying that the field is going from left to right and the current is coming out. But we need to have the current going in. So what we're going to do now is just simply rotate our hand, keeping our fingers the same way. So you rotate your hand, you're going to see the back of your hand. Alright? Now what do you realize about your thumb? Where does your thumb point? Where does your thumb point? Huh?
Upward too.
Upward? Where does your index finger point? From left to right?
Yes, sir.
Where does your middle finger point? In or out? In? And where does your thumb point?
Upwards.
You sure? Left hand you use,
Yeah.
you know. Left hand.
Left hand.
Yeah, left hand.
I want to say what to do with this here.
So, yeah, so your index finger must be pointing from left to right. Your middle finger must be pointing into the page, into the screen, or pointing away from you.
So that means your thumb finger will be left.
No man, the thumb must be right angles, you know, so everything must be right angle.
So which one will point to the screen?
Alright, the middle finger must be pointing into the screen.
Left hand. That means the index will point down.
No man, index point from north to south. You getting it, Reed?
Sir, left hand, yes, sir.
Yeah man, left hand.
90 degrees everything.
Yeah. It working out?
Wait, sir, last time, index finger first.
Index finger must point from left to right in the direction of the magnetic field. What do you see?
Sir. Sir.
Yes, repeat that for me. Repeat what you said now.
Sir, the thumb supposed to point in towards you, sir.
No man, you're not gonna set your thumb. Your thumb will automatically line up. So the two fingers that you should be setting is your index finger and your middle finger. Index finger must be pointing from left to right. So your index finger must be pointing to the right. Your middle finger now must be pointing into the screen. So you might have to rotate your hand so that your index finger is pointing into the screen.
Sir, and then the thumb finger go there down.
Mm.
So, guess go sit down upside down.
Right.
Alright.
So once you line it up, you're going to see that your thumb will be pointing down. So the force on this conductor will be a downward force. So this conductor will move down in the magnetic field. Okay? That makes sense?
Yes.
Now, an easier way to see it, if we consider the current coming out. And these things are, they are counterintuitive. So the current is coming out, right? Once you line up your fingers, your index finger is still gonna point north to south, right? But the current is coming out, so your middle finger is gonna be pointing towards you. So therefore, the force on the conductor will be an upward force, so the conductor will move up in this case. Okay? So that's the basis of the motor effect. Now we can connect a loop or wire, right? And now actually have this rotating, and we can use it to turn a fan blade or the motor of an electric drill or something. So that's the motor effect, right? And we use Fleming's left-hand rule. So we need to, note down this thing about Fleming's left-hand rule. Alright? And continue.
Yes.
Alright, so anybody find any question that we can work on? Anybody find any question? Somebody should have a question on standby ready, to go. Anybody? No question? Somebody talk to me, let me know. Alright, so that's the motor effect. Right? There are some diagrams that your examiner love to ask you about, so let me just kind of share those with you. Usually, we'll give you a diagram like this. So they might say, okay, these are two bar magnets. So north. Let me change it around just to kind of test your understanding. So let's say this is south, this is north, right? And we have a conductor here, and this conductor is carrying current, let's say, into the page. So if the conductor is carrying current into the page, we can use Fleming's left-hand rule again. So in this case now, the field is from north to south. So we might have to kind of bend up our hands and bend up ourselves a bit. So, sorry, this is coming out, my bad. That means that the current is coming out. So the field is from north to south, and the current is coming out. So what we're going to see now is that we have to kind of twist up our hand to kind of align this, so we can actually get it. But what you're going to see now is that in this arrangement, the force on this conductor will be a downward force. Right? It will be a downward force. And again, remember I said that these things are counterintuitive. So the first example we looked at, where the north and the south right here, the current was going in. All I did was replace these, so I changed it from north on this side to south. I basically switch around the bar magnets, and I let the current come out. So the force is going to still be down. Right? Hopefully we see that. Hopefully we get that. If not, let me know, because I know these things can be very abstract when we try to explain them using your ability to pull on your imagination. Okay? But if we twist up our hand and twist up our bodies, we'll be able to get that the force is going to be down, because you want your index to be pointing from left to right. Right? And you want the current to be coming out. So you twist around your hand with the current coming out, and you're going to see your thumb pointing down. So they will oftentimes give you diagrams like this. They might give you one like this now. So same idea. So south right here, north. But in this case now we have a conductor carrying the current into the page. So the current is going into the page. So we line up our fingers, index from right to left, middle finger into the page. So your thumb points upward, so the force will be upward. So this is the force right here, that's the force right here. So we want to be familiar with these diagrams. And oftentimes they will ask you to draw the field lines. So what you will do now, you will have something looking like this. Right? Have something looking like this. Right? And again, they're going to be going from north to south, like that. For this one now, it's going to be a similar thing. Right? A similar thing like that. And these are poorly drawn, so let me apologize for that, but this is just the basis of it. Right? So that's pretty much what you will see. Somebody asked a question. Any question? Could somebody ask a question? Let me know if you guys. So everybody good with this? You have to talk, you know, talk the truth. Everybody good with this? Repeat for me.
If it was 9 to south instead of south to 9, it would be the other way around.
Alright, so let me just correct a statement. So when you say south to north, I mean if it was north on the left side and south on the right side, that's what you're saying?
Yes, sir.
Okay, right. So in that case now, if that was the case, yes, it would be reversed. And the current was coming out on this side and current going in, everything will just be reversed. Alright? Yeah, so that's that. Electromagnetic induction. Right? Electromagnetic induction. Alright? So with electromagnetic induction, what we see is that change in magnetic field induces a current. Right? That's the basis of electromagnetic induction. We see that whenever we have a change in magnetic field, it will induce a current. Right? And more so, or let me say, a current in a closed circuit. Because really and truly, it induces an EMF. Right? And that EMF now, once we have a closed circuit, we get a current. So a change in magnetic field induces a current in a closed circuit. Right? That's the basis of electromagnetic induction. Now, scientists studied electromagnetic induction, and there are two things that we need to talk about when we talk about electromagnetic induction. The first thing we need to know about is we need to know about Faraday law. Right? Faraday's law of electromagnetic induction, but I'm just going to simply say Faraday's law. Right? So it's Faraday's law of electromagnetic induction. Now, what Faraday found out from his research, he found out that the rate of change of magnetic flux, I'm going to give it a technical definition. The rate of change of magnetic flux linkages are linked to a conductor is directly proportional to the EMF, right, across its ends. Right? That's Faraday's law of electromagnetic induction. So, to put that into perspective, we have a bar magnet here, like that. We can call this one the north and this one the south. By the way, you guys have this information up top here. We'll talk about Faraday's law and so forth. We have this. Do we have this?
Yeah, I would say.
Okay. So let me just give you time to kind of, capture what you need to capture down. But in the meantime, let's see if we can just develop this thing. So we have the North Pole and the South Pole. Let me bring this over a little more. So we have the North Pole and the South Pole. Now what we see now is that obviously if we have a North and a South Pole, we're going to have magnetic field lines. Right? Like that. Right? Let's say those are the magnetic field lines going from north to south. Now, if we have a conductor now, we have a conductor, let's say like that, and this conductor is, let's say it is now stationary in that magnetic field, right? We have this conductor stationary in this magnetic field. Now, what we say now is that we're going to have some magnetic flux linkages. Now, magnetic flux are just magnetic field lines. Right? So I could say it's the rate of change of magnetic field lines linked to a conductor. So, what we're saying now, and by the way, before I continue, everybody comfortable? What we're talking about so far? Everybody alright with what we're talking about so far? Who's not alright? Speak up, don't be afraid. Trying to make this thing be meaningful. Jaden?
So define alright.
Define alright meaning that, okay, what I'm saying is making sense and you're following along.
Oh, then yes.
You understand already, obviously.
Okay, yes, as an electrical man, but you know, Mike Ashe? Right? So, let's continue with this then now. So, we have this conductor. This is a conductor right here. Alright? Now, what we're saying now is that when this conductor is in this magnetic field, there's going to be some magnetic field lines linked to it. So, how I like to put this into perspective is I like to say that, okay, the magnetic field lines are those magnetic field lines that will pass through the conductor basically, right? That will pass through the conductor. Now, when it is stationary, there's going to be no change in the magnetic flux linkages or the magnetic field lines linked to the conductor. Now, as soon as we start to move it, there's going to be a change in magnetic flux linkage. Okay? So now, what Faraday said now is that the rate of change of those magnetic field flux linkages or magnetic field lines linked to the conductor will be directly proportional to the EMF, right? To the EMF, or let me just say PD, right? Better to say PD. The PD, right? My bad. PD, the potential difference across its ends. So now, what that simply means is that the faster the conductor moves in the coil, then the greater the PD that will be produced. So the faster the conductor moves, the greater the PD, right? Faster the conductor moves, the greater the PD. Okay? Now, what we're going to see now is that if we connect this wire to, let us say, a circuit like this, and we form a closed circuit, let us say this is a light bulb. So let's say like that. We connect this to a circuit with a light bulb. What we're going to see now is that that PD will now cause a current to flow. And the current that flows is what we call the induced current. So that is why we say that whenever there's a change in magnetic flux linkages, there's going to be an induced current. Now, what we need to also know, be aware of, is that as we move the conductor in the field, we get a current. So the motor effect and electromagnetic induction, I mean, they are, and we're going to see that this is what we call the, what we call this effect, Jaden, where we get a current from magnets and wire. What we call that? When we get a current from a wire and magnets. What we call it?
When you're
No, electromagnet. No.
No, not an electromagnet, man.
What you say?
When we
Magnet
get
and current.
when we get a current
What?
from magnets and wires.
Um,
Yeah, we get
Alright,
induction.
let me put it into let me see if I can help you out. So with the motor effect, where is it? With the motor effect, we're getting motion, right? We're getting motion from the conductor and the magnet. So we're getting motion, that is why we call it a motor. Now in this case now, we're getting current, right? So we're getting current from the conductor and the magnet. So what do we call that? If we're producing something, what are we doing? If we're producing current, what are we doing?
So if we're what?
If we're producing current, when the current gone, right? And you know, if you are so
If we're producing current generator, right?
right, you're gonna generate it, right? So we use a generator, right? Which is
Oh. Oh, okay.
so we see it now,
I see.
right? So with electromagnetic induction now, we basically know this now is what we call now the generator rule or the dynamo rule, right? So we have the motor rule and we have the dynamo rule. So a dynamo is basically a generator, something that actually produces electricity due to motion. So the motor gives you motion due to electricity, while the dynamo gives you electricity due to motion. So this right here is the dynamo effect. Dynamo effect. Right? So that's essentially the dynamo effect. So we move the conductor and we get a current. Now, next thing we want to talk about though, so we said the induced current is what flows due to the induced EMF. Alright, so let me just put a note on that. An induced current flow, an induced current flows due to the induced current flows, let's say in a closed circuit due to the induced you know, I really want to say EMF, you know, but induced yeah, I really should say EMF really, like honestly, when I think about it as I'm now writing this, due to the induced EMF. So I'm gonna go back on my word and put this as EMF because it's really an EMF, right? Really and truly, it's really an EMF, right? Or just a voltage, right? Simply, it's a voltage. Once we talk about EMF or PD, we're just talking about a voltage. So, in simple terms, right? But you know, the physicists, you know, we tend to differentiate EMF and PD and voltage. You know, tend to kind of give them different definitions. All right, so an induced current will flow due to the induced EMF. Now, we want to talk about that induced current. We want to talk about that induced current. So, to talk about this induced current, we have to mention another law. Another law, which is what we call Lenz's law. Right? Lenz's law. Jada, you know about Lenz's law?
Do you remember it as about some direction I current?
Okay.
Different kind induced, not sure.
Okay. Something along those lines. So Lenz's law says that the induced current always flow in a direction such that it opposes opposes the change, the change causing it. Right? So the induced current will flow to oppose whatever change is causing it. So if we consider, let's say we consider in this example that we're moving this conductor upward. Right? So we're moving this conductor upward in this magnetic field. As we move this conductor, we're going to get an induced EMF. Now that induced EMF now will cause an induced current to flow. Now what Lenz's law says now is that that induced current will flow in such a direction such that it opposes the change that is causing it. In this case, the change that causes that induced current is the movement of the conductor. Again, when we move the conductor in the magnetic field, it's going to induce an EMF, right? Induce an EMF across the conductor. Now, because we have that conductor connected to a closed circuit, we're going to get an induced current. Now, that induced current will flow in such a direction to oppose the change that is causing it. And in this case now, the change that causes that induced current is the upward movement of the conductor. So then, what we're saying now is that as we move the conductor upward, that induces a current. Now there's going to be a current that is flowing in this conductor to prevent us from moving the conductor upward. That makes sense? Does that make sense?
So can you repeat?
Yes, so what I'm saying is that based on Lenz's law, the current, the induced current, it will always flow such that it opposes the change causing it. So in this case now, in this example now, if we're moving the conductor upward, we are producing a change, right? We're producing a change. Now that change will induce the current. But the current now will now try to oppose that change. So we moving the conductor upward, the current will flow to prevent us or to oppose us moving the conductor upward. Okay?
Oh, okay.
So that's what Lenz's law says. Now, to determine the direction of the induced current, so for the direction of the induced current, we're going to call on Fleming's again, but in this case, we use Fleming's right-hand rule. Right? And Fleming's right-hand rule is what we call the dynamo rule. Dynamo rule. So, let me see, how can I draw the right hand? Alright, so your right hand is going to look like that. So your right hand is going to basically be the same thing. So, your thumb like that, bam. This one goes out, this one goes this way, and your fingers curl like that. Something like that. Right? That's for your right hand. Now, in this case now, this is your thumb, right? The thumb. However, instead of using the T for thumb, let me write out the word. So this is your thumb. The thumb. This is your first finger. And this is your second finger. So with Fleming's right-hand rule, the thumb, we look at the M, right? The thumb, so the thumb tells the motion. So we look at the M, the thumb tells the motion, the first finger remains the same. So the first finger tells you the field, right? And your second finger now is going to tell you the direction of the induced conventional current, right? Or the direction of the induced current, which is going to be a conventional current. So then, if we go back up to our situation here, so we take our right hand and we line up everything right angles. In this case now, the field is going from north to south, so we have to rotate our hand so that the field is north to south. And in this case now, we are going to line up our index finger and the thumb, and the middle finger will fall in place. So index finger goes from north to south, middle finger goes up. Right? So if you are able to line up yourself, line up your hands and tell me in which direction does your middle finger point.
Goes up.
Huh?
Up.
Alright, so let's go again. So your index should be pointing from left to right. Your thumb should be pointing upward because your thumb is the motion. The motion is that we're moving the conductor upward. So your thumb must be up and your index finger must be from left to right, or in this case from north to south. Okay? With me?
Yes, sir.
So where does your middle finger point?
From back.
Are you using the right hand?
Oh, my God.
Right hand rule, man. Right hand rule. So it's the right hand rule, remember. So Fleming's right hand rule. Malcolm, oh, towards you. Okay? Again, check it the right hand. Right hand, so index must be going to the right.
Away.
Thumb must be going up. So where does the index, sorry, where does the middle finger point now? So check it again, double check it, double check it. Away from you, you sure? Your right hand, you know. Right hand, right hand, right hand. But you have to know your right from your left. So basically, what you should have your thumb going up like that. This is your right hand. This is the back of your hand. Right, your index going that way. Right, and the other fingers, the thumb. What am I talking about? Sorry. Let me go again. So this is your thumb right here. Index gonna go this way. And this is the back of your hand. This is the back of your hand, so your knuckle, like that. Whatever, or your knuckle look. And these fingers now, you won't see these fingers. Right? You won't see these fingers basically. Right? Something like that. Right? You with me?
Yes, sir.
So where does your middle finger point now? Away, right? Away from you. Right? So it's going to be pointing into the page. So your middle finger is going to be going something like that. Right? Something like that. So what we see now is that the current will be flowing into the page. So that will be the direction of the current. It's going to be going into the page. Okay?
Yes, sir.
Now, this is where Lenz's law now makes sense. Because if we now use the right hand rule, Fleming's right hand rule, and we say, okay, where would be the force on the conductor if the current is going in? So the field is still going north to south, the current is going in. So we now take our left hand now. Take the left hand, and where does your thumb point? When you use the left hand rule, consider that the current is going in, and the field is from left to right. Where does the thumb point for the left hand? Where does the thumb point for the left hand? Huh?
Sir?
Yes, where does it, when you apply, huh?
Didn't hear.
I don't hear.
Didn't hear, sir.
What?
I never heard it.
You didn't hear? Oh, I'm saying, we now just said that the current was going in, right, along the wire. So this is the current flowing in. So I'm saying now, let us now use Fleming's left hand rule to just justify that. So we're saying that the current is going in, the field is going from north to south, so left to right, current is going in, right? So the index, left to right, middle finger goes in for the left hand. So where does the thumb point?
Down.
Down. So what it means now is that the force due to the current going in on this conductor is going to be a downward force, which therefore opposes the upward force. So that is why Lenz, right, says that the current will flow such that it opposes the change that is causing it. Alright? Anybody find a question?
Sir, they send one to you in WhatsApp.
In WhatsApp? Okay. Oh, okay. You can send it to like a link or something, so we can just load it on the, because we gotta pull it up.
So it wasn't really a past paper, but like a question from a revision book.
Okay. Alright, okay. Alright, so let's look at it then now. Alright, so we have something like this. So we had, they gave us, let me use the same colors, they gave us something like this. So they gave us this, and they gave us this one. So they gave us something like that, and they said that they have a conductor like this, and it's carrying the current into the page. So this says now, sketch the magnetic field diagram for figure 32A. Alright, so which is basically what we sketched before. So let me just label this up properly. So this is south, and this is north. So now we know that the magnetic field lines always go north to south. Right? North to south. Now, it's two things at play now. Two things at play. Let me, I don't want to make it complex. Two things at play. But essentially, what we're going to have is we're going to have the field lines due to the bar magnet going this way. Right? North to south, like that, north to south. Now, for this conductor now, because it's carrying the current out of the page, we use the right hand grip rule for that. And we're going to see that we're going to grip it with our thumb pointing towards us, and our fingers are going to curl this way, right? So we're going to get our circles going that way. Now, as a result of that now, what we're going to see now is that we're going to have our field. Let me go back, just so I can show you what's happening. Let me use a different color. So here now we're going to have our field lines going like this. Let me just put on 2. So this is the field line around this conductor. Right? Now notice that at the top right here, these yellow lines and these green lines are going in the same direction. So because these forces are going in the same direction, they're going to, remember vectors in the same direction we add. So these two, they're going to add. So the force on the top is going to be great. On the bottom side now, they are going in opposite direction. So the force on the bottom is going to be weak. So as a result of that now, we're going to have the force on the top being stronger than the force on the bottom. So we're going to get this going downward. And we can verify that using Fleming's left-hand rule. However, we can draw the field. So I'm just going to draw the field now to show you what's going to happen. So essentially what's going to happen is that we're going to have the field. They're going to originate here. They're going to go like that. Right? Go like that. Right? Something like that. Right? And on the bottom side, we're not going to have any field present. Or we could just probably show one. Right? Something. I don't like putting any note there. Let me just put it like that. And these are going to be going from north to south. Because what we're saying is that on the bottom, the fields will actually cancel out. But on the top, they're going to get stronger. So as a result of this now, this conductor will move downward. And again, Fleming's left-hand rule will verify that. So we line up our fingers. Index go from right to left. Middle finger comes out. So the thumb will point down. So that's that. Next one on the fly, we're going to have this one now. So they gave us and I mean, if persons have questions, don't afraid to ask questions, because I might be going quick too fast for you. So you have to let me know if something that makes sense. All right, so this one now we have north right here and we have south right here. And this is our conductor now. So this is the conductor, and the conductor is carrying current this way. So based on that now, let's say we must do what? Oh, just for 32A. Now it says, now with the aid of a diagram, explain the function of a, okay, get the magnetic field, okay. So with the aid of a diagram, explain the function of a simple DC motor. Alright, so for that now, we have to get a little complex. So we will draw two bar magnets like that. Sorry. We'll draw two bar magnets like so. Two bar magnets like that, right? And we will draw a loop inside. So we have a loop. It's gonna go like that. I'm kind of going quickly with this, because I don't want us to go too long. So we're going to have a loop like this. We're going to have what we call a split ring. A split ring like that. Something like this. Split ring. And we're going to have our carbon brushes. I don't like how I'm rushing this, because I really feel like I'm rushing it. I really feel like I'm rushing this thing. And I don't know if it's any helpful for me to be rushing it. But let me just double down a bit. Let me just double down. Oh, actually I forgot my registration. Alright, anyways, let me just redraw this and just do it the right way, so we can really make something meaningful of this. Alright, so we will have our bar magnets like this. So that's one of the bar magnets. That's one right there. The other one now is gonna go like so. Let me space this out a bit. So the other one goes like this. Alright, something like that. So that's our bar magnet. And we're going to have a coil. Right? A coil going like that. So that's the coil, right? So we're going to have A, let me just label this A, B, C, and D. Now we're going to have our, as I said before, split rings. So these are split rings right here, one on that side, one on that side. Then we're going to have our carbon brushes. So these are carbon brushes, and this now will be connected to a circuit. Connected to a circuit, let's say like so. Usually we will have not usually, we will have a battery here, and maybe a little switch. Let me just close the switch. So that's that. Now, should I put the switch over here? But anyways, So what we'll see now is that we're going to have a current flowing. So when the switch is closed, or when the circuit is activated, we're going to consider conventional current, which involves the movement of positive charges. So we're going to have current flowing from this end through the carbon brush, through the split ring, and then through the loop. So we're going to have current going in on this side. So current goes in on that side, and then naturally current is going to come out on this side. Now remember that we have to have our magnetic field lines. They're going to be going from north to south like that. Now as a result of that, now the current, the conductor carrying a current in the magnetic field, there's going to be a force, which we can determine using Fleming's left-hand rule. So, using Fleming's left-hand rule. So now, from Fleming's left-hand rule, the current is going in, field is going from north to south. I didn't label this, and north to south. So the field is going from north to south, current is going in. So the thumb is going to be pointing downward. So we're going to get a downward force here. So we get a downward force here. On this side, the current is coming out. So obviously we're going to get an upward force. So these two forces now, they're going to create a couple, which will now cause this to rotate. So let me see exactly what the question says now. Alright, so the question says. So it says that explain the function of a simple DC motor. So this would be the diagram that we would draw. And usually once you draw a diagram, you'll have to label it up. So this would be your bar mag net. This right here. And I'm just using arrows to point, but naturally when you label up, you're not going to use arrows. So this is the coil, C-O-I-L, coil. This now is your external, this is your circuit. These devices now, this one right here is what we call the carbon brush. Right, carbon brush. This pink item right here is the split ring. Right? So those are the key things that you would label with this circuit. So I don't feel like you guys getting this. I mean, I know because I can feel it. Because I know I'm going quickly with this. And again, as I said, it's because I wish not to. Jaden, you laugh, youth. And you have exam Monday. Suppose I say, sir, can you explain again for me? Mr. Jaden.
Sure. Then it was necessarily good.
Yeah, I mean, as I said, like I know it's a tough area, especially the motor. That is why I kind of touch on the motor effect, so that at the very least, you guys can have some understanding as to why it is that the coil will start to rotate. I think I have some questions like this for the marathon. And then, yeah, YouTube as well, and I have some videos. Well, YouTube will actually show the demonstration of the operation. And in the classroom, so for those persons who registered for the marathon and they get access to the resources, you will see past paper questions in which I explain these. So you can, check out those. Now, the next question now says we're to describe how an induced current can be produced in a metal rod. So we must be able to say how the induced current is produced in a metal rod. We just simply say that, okay, when the metal rod is moved in a magnetic field, right, we're going to get a induced current, because we're going to get an induced EMF which will drive an induced current. Now, one thing we also need to be aware of is that the conductor must be moved at right angles, because that becomes useful when we talk about the generator, which we need to talk about, but we're not going to be able to talk about that now. So it says, redraw figure 32, 2. Oh, is that thing that, we can't answer that question there? I don't think it's on this. But it says 3219.
So that's who's in it, sir.
Yeah. Alright, who have question, who have concern, who feel away about this, who start worry, who for either hurt them? What's going on?
Every day, sir, since CXC start, but we can't go on YouTube for this.
Okay. Yeah, man. So you'll find YouTube videos, you know, which actually explains this. In terms of, and they actually have animations. You know, finishing now, you know, just waiting on this last question, from Mullins, because basically I wanted to close it off.
Sir, how much section you think answer for?
How much what?
Section.
5. A to E.
In 5, sir, the first one I graph and it.
But what you have to remember, you know, is that the graph question can come from any one of the sections. They don't necessarily have to come from section 1. Right, the graph can come from any area. So you want to at least know that, you know, you can plot graphs, you know, regardless of whichever area the graph is on, because no matter what the graph is about, it's the same techniques you're using. Drawing the axes, what is it now? Label the axes, choosing a scale, plotting your points, using your dots and circles or your x's, and drawing a gradient, drawing a best fit line, calculating gradient and so forth. So, alright, so let's look at that question, you know. Let's look at that one. So we have something like this. Let me draw this solenoid now. So it goes up in the back, over. Let me just draw it straight. So we have a solenoid. Let me draw it large. It goes like this. That. Right? And we have a galvanometer. Now a galvanometer is like an ammeter. It measures very small current. So let me put it in the middle as what they have. So that's the galvanometer. And we have a bar magnet here. So this is a bar magnet. Right, this is a bar magnet. And we have a north pole right here. And we have a south pole right here. So let's look at this thing now. Buddy, have your attention? Have everyone's attention?
Yes, sir. Well, for me.
Alright? So watch this now. So now, what the question is saying is that what the question says, we draw the north pole of the, so let's look at A first. So we're considering that the north pole is pushed into the coil. So first, we're going to push the north pole of this magnet into the coil. So we're going to push this magnet into this solenoid right here. Now, as we push this magnet in, we're going to have what we call now a change in magnetic flux linkages. Because as we bring this closer and closer, the magnetic field lines are going to now start to interact with the solenoid. So we're going to have a change in magnetic flux, or a change in magnetic field linked to this coil. So when it is far away, we're going to have just a few magnetic field lines linked to this solenoid. But as we bring it closer, we're going to increase the number of magnetic field lines linked to it, linked to the solenoid. Now again, from Faraday's law, right, the rate of change of magnetic flux linkages will induce, is directly proportional to the EMF, right? And that EMF now will induce a current. So as we bring this magnet close to this solenoid, it's going to cause an induced current. Okay? It's going to cause an induced current. Now, based on Lenz's law says that the induced current will always flow to oppose the change causing it. So remember that, you know. We bring the bar magnet in, it induces a current. The current will flow to oppose the bar magnet going close to it. But I appreciate that.
Yes, sir.
So now,
No, wait, sir, repeat.
yes. So as we bring this bar magnet in, it's going to cause an induced current to flow. Now that induced current will flow to oppose the bar magnet going in. Okay? You with me?
Yes, sir.
So now, if it is that the current is flowing to oppose this bar magnet, right? Remember, we said somewhere up here, that like poles repel. So what we're going to see now is that the current that will flow in such a way that it will repel the bar magnet. So if we have the north pole going in, right? What must be here to repel this north pole?
South Pole.
No man, can't be south pole, man.
Wait, no,
North.
North pole, because north and north will repel. So what's going to happen is that the current will flow such that we have a north pole right here, right? So that's what's going to happen. Let's go back to the question now. So it says now, showing, okay, the direction of the current. So they want us to see the direction of the current. So now, once we know that this is a north pole, all we do is we're going to use Fleming's, what's the guy name? Fleming's, not Fleming's, my bad, the right hand grip rule. All we're going to use is the right hand grip rule. So what we're going to see now is that with the right hand grip rule, we're going to place our hand over the solenoid with the thumb pointing towards the north pole. So our fingers are going to be curling towards us. So therefore now that's going to represent the direction of the current. So what it means then now is that the current is going to be, so since our fingers are curling down, the current will be flowing down in the front. So down like that. So let's see, this is the front. Let me start over here. Because it goes up, this is the front, so it's going to go down like that. Down, 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 and down. Right? So that's going to be the direction of the current. So the current is going to be flowing down this way. So if we continue, so if the current is going down this way, it must be going up here. So the current goes up, up, down, around, around, until it eventually leaves right here. So what we see now is that if that's the case, then now the needle of the galvanometer, it always points in the direction of the current. Because sometimes they ask you that. I don't think this question asks that, but sometimes they might ask you that. So the needle of the galvanometer will go like that. Okay? That makes sense?
Yes, sir.
Now the next question now says that the pole of the magnet is left at rest. So if the pole of the magnet is left at rest, what's going to happen is that no current will flow. So the needle of the galvanometer will go back to the middle. And all of these will be removed. Let me just remove them. Just remove them one by one. So once there's no movement, so in order for us to induce a current, there must be either movement of the magnet or movement of the coil. So when the bar magnet is stationary in the coil, the needle will come back to the middle right there. Then now it says now that the pole of the north pole of the magnet is withdrawn from the coil. So in other words, what we're saying now is that we're going to be moving this bar magnet away. So as we move this bar magnet away, the change in this case now is that the north pole is leaving. So if the north pole is leaving now, what are we going to do to oppose the north pole leaving? What are we going to place right here?
It's South Pole.
A south pole. So you see how this induction thing work? You know, we insert the bar magnet and the coil is preventing the bar magnet from being inserted. Right? Then as soon as you say, alright, let's just move away the bar magnet. The coil now saying, okay, no, don't leave. Right? What does that sound like? What does that sound like? Does that sound like some female sometime? you know, you're giving them attention and, you know, they're pushing you off. And then as soon as they say, all right, you know, you see them come around. All right? So it's the same thing taking place right here. So we're moving the North Pole and the coil set up a South Pole right here to prevent the North Pole from leaving. So now, as a result of that now, we're going to see that, okay, if this is the South Pole, this is going to be the North Pole. And again, we place our hand, right, and we're going to see now that the current is going to be, so in this case now, this is the current is going to be going, so current is going to be going up in the front, so it's going to be going this way, up in the front, right, and down in the back, in this case. Sorry, my bad. All right, so let me just go again. All right, so it's going to be going up in the front, down in the back. So if we're saying that these are at the front, this is going to be the back, so it's going to be going down in the back. So down like that, down, down, down like that. So what we're going to see now, is that the direction of the current now will be reversed, because the current is going to be going down here, and it's going to go up in the front and leave like that. So therefore now what we're going to see now is that the galvanometer will now point in the opposite direction. So what we see now is that when we were placing the bar magnet into the coil, the current flowed in a particular direction. Then as we remove it, the direction of the current reverses. So from that now, that is how we produce alternating current. Okay, by that constant change in direction. So I'm hoping we would have been able to somewhat there is an attack, Michael shit. So, you know, hopefully we will somehow be able to get something from this session. I'm going to send out the recording so persons can rewatch and so forth. Yes.
So you can send the document to say.
Yes, I'm gonna send it. Alright, so that's that. So we close off here. So for those persons who will be here tomorrow, Jaden, you'll be here tomorrow?
Yes, sir.
Alright, Malcolm?
So you mean face to face?
Face to face, yes, for the marathon.
I think so, sir.
Right? When you say think so, what do you mean? Because I need to finalize the list, you know, from tonight. So I have the papers printed and everything.
I would have to ask my parents.
Yes. And so ask them and confirm so I can know. Right?
Alright, sir.
Alright, because we're going to be working, so just like how we're working the questions here, we're actually going to get the papers for you to write out and you know, you can take home and use that as revision. And we're going to touch on questions from all areas. Right?
Okay, sir.
Yeah, man. Alright, so we close this and we continue. Well, for those who come in tomorrow, we'll continue tomorrow, and then those who will be here Sunday, online Sunday, will continue on Sunday. Alright, so that's that.